Finally on to redox titrations, which in most aspects are pretty similar to acid-base titrations. You need a clear colour change occurring near the equivalence point. Now, getting a colour change excuse me, is the problematic thing. Two ways to get it. One is to use a coloured chemical, coloured oxidising agent or reducing agent, and potassium permanganate, potassium dichromate are the two classic ones of those. Potassium permanganate has a really intense purple colour, and when it's in excess, that colour is going to be clearly evident. So you're looking for that colour to appear or to disappear. The other way, there are indicator systems. If molecular iodine is present, a starch indicator will turn blue-black. So you go from the straw, yellowy, browny iodine colour to a really intense blue-black colour as soon as the iodine is in excess. So let's run through an example. So what have we got? We are analysing ascorbic acid, vitamin C. So we crush 2 tablets. Interesting fact that it's 2 tablets, and total mass 2.5 grams. We dissolve the whole 2.5 grams in 50 mils of sulfuric acid. Now the sulfuric acid is not necessarily a reactant, of course it's a redox reaction, so we've got to have things in acidic environments. And we are going to titrate all of this solution. So there's no dilutions happening here, we're just going to titrate all of the vitamin C in our 2 tablets with iodine solution, and we get a titer of 19.65 mils. So the titration itself is a very simple one really. Then we'll just have to work back through the amount of ascorbic, the number of moles of ascorbic acid to the mass to what's in the original tablets, percentage by mass in the tablets. So aim, percentage by mass of ascorbic acid. And oh yeah, the mass of ascorbic acid in each tablet. Note that we're given the mass of 2 tablets. We want the mass of ascorbic acid in each tablet. At some point we're going to have to halve our answer to get that. That's a little trick they've put in for the unwary. Diagram. Now, diagram is always good. This is a fairly simple one if you can see what's going on. That's all good. So we've got all of the vitamin C going into some sulfuric acid, dissolving it all, and then we're titrating it all. And we've got our information about the standard solution. So we've got our equation, and all we're after in the equation is the mole ratio, and we see it's a 1-to-1 mole ratio. As I say, ignore the sulfuric acid. It just dissolves the tablet. And the 3 basic stoichiometry steps. Amount of standard solution, number of moles from of the standard solution, what have I got to get moles of the unknown, it's 1-to-1 mole ratio, and then the mass of the unknown, but remember we've got to divide by 2 because it's just 1 tablet. Then our final step is to turn that into a percentage by mass. So we know that the mass of both tablets was 2.5 grams. So the total mass of ascorbic acid has to be used, 1 by the other times 100, and we get 8.22. So I might go through both of the examples at this stage, then set you both of the questions. So, example 2. Okay, we're catching up with some environmental crooks. They are chucking their acetaldehyde into the creek. And what do? We got a 50 ml sample of wastewater, diluted it to 250 mils. We've got a dilution there, 50 to 250, dilution factor of 5. We then titrated 20 ml aliquots of it with standard potassium permanganate, and we've got some products. We've got 4 titers, and we've got a bit of work to do here. So let's go. So the first thing to do is work out that average titer. Which of these 3 are concordant? Which 3 of these are concordant? Well, that's the top one. We don't have 3 within 0.1 of a mil of that. That's the bottom one. We do have 3 within 0.1 of a mil of that. So we exclude 11.14. Calculate our average titer. Next, of course, is the inevitable equation. I'll chuck in redox equations at any random part of this course, and here's another place where they can do it. So, skeleton equation, you're given the chemicals, permanganate and acetaldehyde, manganese 2, and you know what happens when aldehydes are oxidised, they turn into carboxylic acids. So that's going to be our skeleton equation. Now we have to separate those out into the 2 redox half equations. Don't try and do this as an overall equation, you'll stuff it up. So oxidation is acetaldehyde to acetic acid, ethanoic acid. Now we've got the number of carbons, of course, balanced. So next thing is to balance the oxygens by adding water. Next thing is to balance the hydrogens by adding H+. So what have we got on this side? We've got 6 hydrogens, we've got 4 hydrogens, so 2 H pluses on the right hand side, and where the hydrogens go, the electrons will go to balance the charges. Then onto the reduction equation, we've got permanganate going to manganese 2. So first step, balance the oxygens by adding waters, 4 oxygens, 4 waters, then 8 hydrogens, 4 times 2 means 8H+. Then being a little bit careful when we do our numbers, we've got -1 plus 8 gives +7, so +7 down to +2 means 5 electrons on the left hand side. Then we combine them into an overall equation. So we've got to cross multiply. We'll multiply the first equation by 5, the second equation by 2, and then combine. Now when we get there, we'll see we've got waters on both sides. So we've got 3 more waters on the right hand side, so we can have 3 waters over there. We've got extra 6 hydrogens on the left hand side, so they'll go there. Electrons, of course, will cancel out. That's what we end up. Of course, when we get to write the equation, we will include states, because these are the sorts of equations which are liable to require you to do states to get the mark. So do the 2 redox titration questions and I'll email you the link to the solutions. Submit them online, of course, as always, and then check your answers.